like 2 weeks from now, I will feel like so good.
Yeah, you know, there's stuff to do for some.
Oh my God. That'll be good.
Yeah. The real house gotta survive and some of them.
That's why I'm gonna eat a lot of food and take a nap.
I feel that. It's it's gonna be a ball. Get like the 500 pounders. It's coming to damn steel.
I would not be made of steel.
After
Made
the
of fucking dough.
that's like roll.
You have to roll me in this. I guess.
Okay, so today we're gonna do this last thing, Laplace transforms. It's really gonna be a little bit, it's gonna take a couple class periods, so literally like probably the next class, to work with what is the definition of a Laplace transform. And eventually, you're not gonna see this immediately, but we're gonna connect it to how to solve a differential equation. So this is going to be another method on top of everything else that we learned. It turns out that many of those equations we've done in the past, we could have also done Laplace transforms for. So this is yet another type of technique. And the definition of a Laplace transform is really just an improper integral. So for today, and likely maybe the next class as well, will be a lot of Calc 2. You've seen integrals. And in particular, improper integral is if you have a bound that's infinite. And so, there's questions of, does this integral converge or diverge? Because you're integrating all the way off to infinity. So whenever this integral is defined, provided that this improper integral exists, that's the Laplace transform. So there's a function. What you're doing is you're taking the f of t, is your function, and you're trying to take the Laplace transform of it. So the Laplace transform of f of t is like taking that f of t function and multiplying by e to the negative st and differentiating with respect to t. This s isn't the variable that you're integrating with respect to. You're integrating with respect to t. So in the end, s stays. T gets integrated out because you're going to plug in infinity and then 0 for the t. But s will remain. So therefore, your Laplace transform, your function, is going to be a function of s. And you could write it like this, where you have a fancy L, f of t. But many people also write it as capital F of s. The little f is for the original function. Capital S is for the Laplace transform. And then s is the variable that remains after you take this integral with respect to t. And so if you have your function is f of t, then it's capital F of s. If your function is little g of t, then your Laplace transform is capital G of s. If it's y of t, then capital Y of s. That's the notation that they like to use. Okay, this is the definition of Laplace transform. It's just taking the function f of t, multiplying by e to the negative st, take the integral from negative 0 to infinity. Let's do a Laplace transform of something really easy. So the Laplace transform of 1 is, so I also mention that this s actually has a name. It's called the transform variable. So the Laplace transform of 1, well, in this case, my f of t is just equal to 1. So basically, yeah, this f of t here is just equal to 1. So you're going to take the Laplace transform of 1. The Laplace transform of 1 is just using the definition, the integral from 0 to infinity of e to the negative st times, I could just say 1, because that's like our function, with respect to dt. Okay, so this is just taking the integral from 0 to infinity of e to the negative st dt. And you may have learned this in Calc 2. You just say the limit as b goes to infinity of b0 e to the negative st dt. Because one of the bounds is infinite. Think of it as a limit. And what you're going to do is you're going to take the integral of the thing. B goes to infinity. The integral, just have to be careful here. You're integrating with respect to t. So s is like not the variable. So the integral is do you see, let's go backwards. So if I were to take the integral of the derivative, if I were to take the derivative of this, S acts like your constant. S is like acting like your constant because t is the variable you're integrating with respect to. So if you were to take the derivative of e to the negative st, the derivative of e to the negative st would have been chain rule, negative s times e to the negative st, but this doesn't have a negative s in front, so you have to divide by negative s. Think of s as like 2 or 3 or something like that. It's acting like a constant, right? So now this is the integral, the antiderivative, and so you'll say we're just interested in computing this definite integral means that I'm going to do the limit as b goes to infinity of e to the negative st over negative s. And then I'm going to subtract from it e to the, we're going to plug in 0, so it's going to be e to the 0 over negative s. The 0 goes only into the t, so e to the 0. So this is just going to be the limit as b goes to infinity of e to the negative st over negative s. This is e to the 0 is 1. There's 2 negatives, so it'd be plus 1 over s. So the only issue is this limit right here. This limit right here, we have to be careful. The other thing is we got to make sure, like it's set up here, provided that the improper integral exists, right? So the Laplace transform is this, provided that the improper integral exists. This is asking you to also determine its domain. So from the second term right here, we know that s can't be equal to 0. The domain of our Laplace transform is a function of s, and the domain of that, for this to exist, we need to make sure that s doesn't equal 0. Did you have a question, Sebastian? No, you were just stretching. So this is an improper, this is a limit we have to compute. So we're going to check what happens to this integral right here, this limit. I'm going to make some observations here. So s, this limit diverges if s is, so it depends on what s is. So if s is less than 0, versus if s is greater than 0. Let's think about what happens. If s is less than 0, then this is going to be e raised to like t is going to infinity. I guess I should have said not t, but I should have said this is b. Because what we did was we plugged in b for t. This is b. So if we're letting b go to infinity and s is negative, then it's going to be negative of a negative and then infinity. So it's going to be e to the positive infinity divided by, down here, if it's s is less than 0, then it'd be negative of a negative number. So this is some positive number. But this is going to be like infinity, because this is e raised to infinity over some positive number. This is diverges. So we know that for this improper integral to exist, we can't have s be less than 0, because this limit will diverge if we had s less 0. What about if s is greater than 0? If s is greater than 0, then you're going to have e raised to some positive s times infinity. So it's going to be e to the negative infinity, which is just the opposite of this. The bottom here is going to be s is greater than 0, so negative s will be some negative number. But this is fine because it's really just going to be 0, because e raised to negative infinity is like really, really small. Divided by some negative number isn't going to have any issues. So this is going to convert, limit exists. Not only does the limit exist, it's going to equal 0. So in the end, we have, this is going to equal, from what we just did down there, 0 plus the 1 over s. And of course, that just means 1 over s. So the Laplace transform of 1, is just equal to 1 over s. Provided that we can't have this, s can't be less than 0, s has to be greater than 0, and s can't be equal to 0. But the combination of this means that s has to be greater than 0. So basically, we know that the Laplace transform exists, and its domain is going to be when s is greater than 0. So the Laplace transform of 1 is 1 over s, and then the difficulty here is you're computing this improper integral, and examining what s is will make this improper integral exist. It means not diverge. And for this improper integral to actually converge, and it'll converge to 1 over s, requires that s is greater than 0. So it's just calc 2. You're just, but maybe it's a little harder because you have to, there's another variable s in there that you have to think about and try to find the domain of s that causes it to converge. Let's do the Laplace transform of t. So now our f of t is just t. This is just saying my f of t is equal to t. So we're just doing the same thing. We're just going to say the Laplace transform of t is like just computing this improper integral. You're going to say 0 to infinity of e to the negative st times the t, it's the function, dt. For this one, you're going to have to do integration by parts. I'm going to use, you could use u is equal to the t, and dv is equal to e to the negative st dt. Then I'm going to, what this ends up becoming is I'm going to integrate the e to the negative st, which is going to be integrated with respect to t. So we're going to treat s like a constant. So it's going to be like negative 1 over s e to the negative st, because the derivative of this will pop out a negative s gets canceled with this and give you that, times the t. And then you're just going to look at this from t equals 0 to t equals infinity. Minus, well, it's going to be a plus because this one has a minus already. 0 to infinity of, now I'm just going to take the this guy right here, 1 over s e to the negative st, and then take the derivative of t, which is just 1, so I don't have to write that. All right, that's just the integration by parts on this improper integral. All right, so now this is going to equal, just write it like this, it's going to be negative 1 over s. I'll just write it like this. The t and the s will combine and just write it as t over s e to the negative st. And still going to take it from 0 to infinity. This right here, because you're integrating with respect to t, this 1 over s is like a constant. So I'm going to pull that out. Okay. This integral from 0 to infinity of e to the negative st, we did just before, because it was really the integral from 0 to infinity of e to the negative st was actually the definition of the Laplace transform of 1. We found that that was 1 over s, and s had to be greater than 0. So we already saw from just the previous previous page that this is equal to 1 over s, provided that s is greater than 1. Otherwise, it diverges. So it's 1 over s. The only one is this one. You have to be careful about this one. So if you're interested in computing this limit right here, let's write it out what this is. This is like saying plug in infinity into this. So it'd be like negative, I'll put negative out and then say limit as, let's say t goes to infinity of, it's going to be like t over, I'm going to put the e to the negative st on the bottom. So it'd be s e to the negative, e to the positive st after you put this in the bottom. Minus, we're going to plug in 0 into this So, well, it's like minus of a minus, so it's a plus. And then it's going to be 0 times e to the 0, which is 1 over s. So it's going to be 0 over s, which is just equal to 0. So really, this thing right here is just equal to this. Okay, now this limit, let's just check. When s is less than 0, we're going to have the t goes off to infinity. So the top is going to be, so I'm going to put the negative is out here. It's going to go to negative infinity because t is going to infinity. Down here, s is negative. So it's going to be a negative for the s, but e to the negative st. So it's going to be like, I'll just say s e to the negative st, negative infinity, right? Because your s is negative and t is going to infinity. So it's going to be e raised to negative infinity. It's going to be negative infinity over s is some negative number. And e is going to be some really, really small number. So it's like going to be like negative with a minus, I guess. But you're just taking some huge number and dividing by a really small number. So this is going to go to infinity and this diverges. So we can't have s greater less than 0. We actually couldn't have it anyways because this would have had issues already, right? This already would have diverged if s was greater than 0. So we know that we for sure can't have it anyways. Well, the only thing we have to confirm is that this piece right here converges only when s is greater than 0. This piece better also converge, otherwise we have like we don't have a Laplace transform exist at all. So let's look at what happens when s is greater than 0. We're looking at this right here. So it's going to be like negative infinity over some s that's positive times e to the s times t. But because s is positive times infinity, it's going to be e to the infinity. This is going to be negative infinity over infinity. Okay, so that's indeterminate. We'll have to do L'Hopital's rule. So if you do L'Hopital's rule, it's going to be like taking the derivative of the top. So you're going to say limit as t goes to infinity. Derivative of t is 1. And the limit we're interested in is computing is for t goes to infinity. So we're going to take the derivative with respect to t, which means that s is like a constant. So s gets popped out because of the chain rule. It's going to be s squared e to the st. And then what is this limit? This is going to be t goes to infinity. So there's only a 1 up here. E to the infinity is going to be down here. So it's going to be 1 over infinity. 1 over infinity. So it's like 1 over infinity. I guess you could put a negative in front because there's a negative there. It's going to be like negative 1 over infinity. But that's just like 0. So s equals greater than 0 will converge. And not only will it converge, it would cause this piece to equal 0. So it'll just be 0. Plus the 1 over s. There's a 1 over s right here. And this integral right here, we computed before, was 1 over s. So in the end, this is 1 over s squared. Provided that, again, s is greater than 0. So the Laplace transform of t is 1 over s squared. And the domain of that is going to be when s is greater than 0 is the only way that this improper integral will converge. Otherwise, it would diverge and not exist. So those are a couple of simple Laplace transforms, but it's just like computing an improper integral and making sure that you set s to be in such a way that the integral will actually converge. Otherwise, the Laplace transform doesn't exist for other values of s. And these are just sort of improper integrals. Always break it down into like the limits, and those limits are going to be sensitive actually to what your s is. They're not always going to actually converge. It depends on whether s is positive or negative usually. And that's what you'll check is usually if it's positive or negative if you were to see. Let's do the Laplace transform of e to the at. E to the at, the f that we're using, the f of t is going to be e to the at. So when you're computing the Laplace transform of this, I'll just be lazy and just say, okay, this is my Laplace transform. It's going to be 0 to infinity of e to the negative st. But now our function is e to the at times integrated with respect to t. So it's just using this definition. It's really just applying this definition. And it's going to feel like we're not doing any differential equations. We're just doing calc 2. What I'm going to do with this one is something clever. I'm going to say that this exponential could keep combined into a single exponential. And I'm going to write it as a negative, wait, did I do? I guess I didn't. Okay. Let's do this, negative s minus a t. It's a kind of a little bit of a weird way of writing it, but if you combine this into a single exponential, you can add these two exponents. They'll both have t common, and I pulled out a negative, so it's going to be negative s minus negative of quantity s minus a t. There's a reason why I wrote it like this. These are equivalent. Once you you could even distribute this -1 negative to the s and this negative to this a, and it'd be like these two terms. But what I'm going to do is I'm going to observe that what did we find earlier? We found that, let's just say, we found that this integral right here, 0 to infinity of e to the negative st dt was equal to 1 over s, I guess, provided that s is greater than 0. So you see this integral right here. We did all this work, but we found that it was equal to 1 over s. We actually can use this result. So I'm going to copy and paste that down here. So here we go. We're going to use this. So what I'll say is we have it's not letting me. What is going on? Okay, let's look at. It's my computer is completely frozen. Let's see. So this works. I don't know why my computer is. So then how can I not switch to Notability? Okay, here we go. Okay, let me just force quit Notability. It's gonna write yes. Okay. Now let's share my screen again. Okay, sorry about that. My Notability just stopped, so I had to force quit. All right, so if you look at this, you see what is going We'll do this. Okay, it works now. Hopefully. Share this. Okay, when you look at this, e to the negative st, this s right here and this right here, these are like the same things, right? So if you look at this, anytime I had e to the negative st, the Laplace transform 1 over was equal to just 1 over s. Looking at with that same pattern in mind, what do you think the Laplace transform of e to the what do you think the integral of e to the negative of quantity s minus a t would be? Yes, exactly. And here it said s had to be greater than 0. Here s had to be greater than s minus a has to be greater than 0, which is the same as s has to be greater than a. And that'll be true. I mean, you could go through the process of computing, this improper integral, which basically means doing this exact same thing, but all the s's will become s minus a. And the conclusion would still be the same as what we just observed, is that basically anytime I have e to the negative of something t, it's 1 over s, where s greater than 0. And that same structure is apparent here. So this is going to be just 1 over s minus a. And it's always a good idea to reuse results you had before. And actually, these first couple ones, we're just doing it by hand, but eventually we're going to be reusing all these results and just applying them rather than actually computing the improper integral by hand. If you have a piecewise function, then the Laplace transform is still like the same as what we had seen before. It's just that it's going to break up into different pieces. So you have to integrate from 0 to infinity, but the function is going to be different for each of those pieces. So you'll first integrate from 0 to 2, but between 0 and 2, our function is just 0. So it's going to be like e to negative st times 0 dt. Then your next integral is going to go from 2 to 5 of your function, your integral, your function you're taking the Laplace transform is 2 for that interval. And then the next is going to be from 5 to infinity. And over that interval, your function is equal to 0. And right off the bat, this is just integrating 0 times this is going to be 0. And so if you're integrating 0 over some interval, it's nothing. And same with this. So the only thing you're left with is just this integral right here. That is cool. Today is not a good day. I probably should restart my computer, but I like to just restart Notability over and over again because apparently it's not letting me. So now you're just computing this integral, which is like just taking the 2 can come out because there's a 2 there. And you're just going to take it's going to be e to the negative st over s, negative s. And then that's going to be evaluated. This is not going to require any limits or anything. It's just t goes to 2, t goes to 5. And so it's just going to equal 2 over s e to the, since they're subtracted, I'll just do this side first. So be take minus e to the negative 5s. And this is defined for all s's. There's no issue. There's no convergence issue because the integral of that was actually going off to infinity was 0. So this is defined for all s because it's just an integral, definite integral from 2 to 5 of this function. And it's going to be fine for any s. This is an s, by the way, is down. So that one's just applying the definition of the Laplace transform onto a piecewise function and breaking up the integral from 0 to infinity into each of these regions because the function actually is piecewise and is different for between 0 to 2 to 5 and 5 to infinity. So that's it. That's just the Laplace transform. So it's just like computing an integral. Now, if you had to take the Laplace transform of multiple things added together, it's no different from what we had before. It's just going to be that now our function f of t, I guess it just doesn't like me to change colors on my pencil because every single time I change my colors, it will. See if I use my mouse instead. It just sticks whenever I do that. So let's just, is this going to work if I do this? Right, so maybe I'll just have to be very careful. Change colors. I'm so used to seeing this. So this is like my f of t. So when I take the Laplace transform of this, it's going to be the integral of 0 to infinity of e to the negative st. That's like, what multiplies with the entire function. So the entire function in this case is all of this stuff. So I'm going to just use blue. 3e to the t plus 5 e to the negative 2t plus 6. And then this is going to be integrated with respect to t. But we know that integrals can split because of linearity, right? So because of linearity, we know that the integral can split into the integral of, so we know from, the calc 1 probably, basically, we know that if you had the integral of C1, f of t plus C2 g of t dt. This is like you could split it as C1 f of t plus the integral of C2 g of t dt. Same idea. So this would be like taking the integral of this times this, this times this, and this times this. So really, it's the same as if you were to just take the Laplace transform of 3e to the t plus the Laplace transform of 5e to the negative 2t plus the Laplace transform 6. The Laplace transform of 3e to the t. Again, you can pull I guess I could even say this actually, because of linearity, we could have pulled the C1 out. So C1, you could have also done the same thing here, C2. So same idea. This is really like the integral of e to the st times 3e to the t, but the 3 could have been pulled out. So that means that this is equivalent to the Laplace transform of 3 times the Laplace transform of e to the t plus 5 times the Laplace transform of e to the negative 2t plus the Laplace transform of 6. Okay, we just did the Laplace transform of e to the t. In a way, we did it because before, we actually did it for a more general case. We found that Laplace transform of e to the at is equal to 1 over s minus a. That's actually right here. Okay, this is a table that's giving us all the results. We also found the Laplace transform 1 was 1 over s. We found that the Laplace transform of t squared was 1 over t squared, 1 over s squared. This one's actually giving you it for t raised to any n. So using this result, what is the Laplace transform of e to the t? Yes. That's just because a is equal to 1. Plus, what's the Laplace transform of e to the negative 2t?
5 over 1. 1 over x plus 2.
Yeah, it's plus 2, because it's really negative of negative 2. And then I guess this one, I could have just said the 6 could have pulled out, so why don't I write that? It could have been 6 comes out, and it'll be just a Laplace transform of 1. And it'll be 6 times the Laplace transform of 1, which is going to be 6 over s, because Laplace transform of that. So basically, this is going to be 3 over s minus 1 plus 5 over s plus 4 plus 6 over s is the Laplace transform of these. So this is just an integral of e to the negative st multiplied to all of this. But you could split this into 3 separate integrals, right? Because of linearity of integration, the constants can get pulled out. And so it decomposes into just 3 times the Laplace transform e to t, 5 times the Laplace transform e to negative 2t, and 6 times the Laplace transform of 1. And we looked at both of those cases. We know Laplace transform of 1 is 1 over s. We know Laplace transform ae to the at is equal to 1 over s minus a, just that the a is different now. It could be like 1 or negative 2 or 3 or something. Okay, so this is like a property that's just follows from the fact that integrals are linearity of intervals. Yes.
Is the 5 over s plus 4?
Oh, sorry, plus 2. Plus 2. Okay. That's fine. So let's do the same thing with this one. This one, again, we're just going to shortcut it. We know due to the linearity of integrals that this is just going to be the Laplace transform of t squared minus, I'm going to pull the 3 out because that would have been a constant in the integration, Laplace transform of t minus 2 Laplace transform of sine of 3t. Okay. So there's only one of these that we actually computed before. Laplace transform of t was this right here. We did this one, and we got that was 1 over s squared. So the Laplace transform of t is 1 over s squared. So we can say that this is going to equal like negative 3 over s squared. But the question is, what is the Laplace transform of t squared? How do we get the Laplace transform of t? We ended up doing integration by parts. We said u is equal to this and dv is equal to this. If you had t squared, you'd have to do integration by parts twice. And the book does that and then does it like for t cubed. And then they say there's a recursive formula that shows up. I'm not going to do that because we're running out of time. But you can look at that in the book. They do it for t. We did it for t squared, and then t cubed. And they say there's a pattern. And then they say this pattern will persist. And so the conclusion is that when t is raised to some power n, the recursion is going to give you n factorial over s raised to n plus 1. And you can read the textbook. The n factorial comes out from just recursively taking, you're going to still probably use, this dv is going to be this piece. U is going to be the t squared. So you're going to integrate this and differentiate the t. And you're going to keep differentiating until the t becomes a constant. But each time you do that, if this was a squared, the 2 comes down, and then the 1 comes down, or 3 comes down, and 2. That's why you get 3 times 2 times 1. And that's where the n factorial is coming from. But, it's worth looking if you wanted to check. We could confirm that what we had before was consistent with this recursion. So when it was just t and was equal to 1, we'll get 1 factorial over s1 plus 1, which is equal to 1 over s squared. And this is what we got before. Now, if we're interested in t squared, that's n is equal to 2. This is going to be 2 factorial over s2 plus 1, which is going to be 2 over s cubed. And that's what we're going to use. So this is going to be 2 over s cubed. And then you're going to have minus 3 s squared. And then this one we for sure didn't do. We didn't do sine of 3t, but I'm giving it to you right here. So, oh crap, again, I made a mistake. I was supposed to not do what I just did because my notability is very sensitive to color changes right now. just crashes whenever I do a color change through my tablet to do it through my mouse. Okay, so this one is going to be 2 over s cubed. And then we said that this is going to be minus 3s squared. And then this one's going to be minus 2. And looking at this table, I'm not going to change colors. I'm just going to be black the whole time. What is going to be the Laplace transform of sine of 3t? Do you think? This is saying sine of bt is equal to b over s squared plus b squared. Yeah, it'll be 3 over s squared. I'll just write it as 3 squared. Okay, which is 9. Yeah. And so do this carefully. I can still at least that's it. That's the Laplace transform. The only one that we didn't do was technically we didn't do the Laplace transform for t squared, which would have required integration by parts twice. The book does it. This is the recursion formula for t raised to n. So we could now use this for t raised to 3 or t raised to 4. It's just this. The Laplace transform to s sine of bt is going to have to try to take the improper integral with f of t being sine of bt. That one is going to be a little bit more work. And the goal was that I would be able to show that, but because of my computer being weird, maybe I won't get a chance to, I might be able to set the stage. I'm going to do let's say the Laplace transform of cosine of bt. The issue with the Laplace transform of cosine of bt is that we don't know how to, so we know how to compute the Laplace transform of something that is just exponentials. So we're going to use that idea. So we're going to say e to the I bt. I'll probably just write whatever I can for now and then just post the rest. Cosine of bt plus I sine of bt. And then I'm going to also do the negative. And this is the only part that's tricky about this. The rest I think you can follow if I this is just using the Euler's formula. So I'm going to say cosine of, this is negative bt plus I sine of negative bt. And this is going to equal cosine of bt because the cosine function is even and the sine function is odd. So I can pull the negative out. And then there's this clever thing you notice. You're going to notice that if I were to add this plus this, you'll have this plus this, but these cancel. This I and this goes away. That's the reason why people like to do this. So then we end up getting that this is just the same as e to the I bt plus e to the negative I bt is equal to 2 cosine of bt. And then if you were to just, so then we know from this that cosine of bt is equal to these exponentials divided by 2. So if I wanted to take the Laplace transform of cosine of bt, this is the same as taking the Laplace transform of this giant thing, which is the same as, I can pull the half out, and it'll be the Laplace transform of these two things on the top. So it'd be the Laplace transform of e to the I bt plus the Laplace transform of e to the negative I bt. And we already know from before that it's going to be half. What's the Laplace transform of e to the I bt? Your a is equal to ib in this case. So it'd be s minus ib. And then this one's going to be 1 over s plus ib. These are complex. But if we actually combine it into a single fraction, the common denominator will be s minus ib and s plus ib. This one is missing an s plus ib. This one is missing an s minus ib. And so if you multiply out the top, so we should just FOIL the top out, it's going to be half over, and we'll also FOIL the bottom. The top is s squared. These cancel, and then you have these two, so be s squared. This is ib times ib, but there's going to be negative I plus, and so it's be b squared on the top. Or actually, did I do a mistake here? Over s. Oh no, I had to do plus, sorry. I had to do plus. This is s plus ib, and then we have to do s minus ib. So the top will just become 2s. And then the bottom is going to become s squared plus b squared. And the 2's cancel, so be s over s squared plus b squared. So yeah, when you combine the two fractions, you're just adding them. So you're going to say this one's missing an s plus ib, so we'll add that. Plus this one's missing an s minus ib, so you add that. And so this is the Laplace transform of cosine of bt. And that's actually, this actually right here, right? The cosine of bt1 is s over s squared plus b squared. The sine bt is very similar. I'll just post it. It's pretty similar. So sorry about my computer. I'm just going to restart my computer.
Laplace.